unfold.
Welcome to the Deep Dive, where we tear apart the source material on the most ambitious projects shaping our future, giving you the essential knowledge fast. Today, we are deep diving into the calculus of the ultimate one-way commitment, Starship, and the audacious mission to Mars.
And this is so much more than just a technical discussion. It's really an exploration of limits. We've synthesized a huge stack of sources today, and they cover everything from the unprecedented engineering behind the ship itself to the crushing biological and psychological tolls of that 6-month transit.
And the philosophical stakes, which are profound.
Yeah.
I mean, the whole question of deciding to make humanity a multiplanetary species.
Exactly.
So our mission here is to distill this massive body of research. We need to understand not just if this is possible, but how this incredible risk equation even begins to balance out. And there's really no better place to start than the physical contradiction of the vehicle itself.
Oh, yeah.
Just think about it for a second. We are talking about this monolithic structure, 121 meters tall, built of industrial-grade 304L stainless steel, the stuff you use for tanks and silos.
Right.
And it's designed to generate nearly triple the thrust of the legendary Saturn V moon rocket.
It truly is. It's an engineering rebellion.
So let's unpack this scale, starting with Section 1. When you look at the Starship stack, the Super Heavy booster mated with the Starship spacecraft dominating the South Texas coastline, its presence is, well, it's intimidating.
It is. It stands 121 meters or 397 feet tall. And it doesn't look like the sleek, expensive, white rockets we're used to seeing.
No, not at all. It looks raw, industrial, almost brutalist.
And that sheer presence immediately challenges, decades of orthodoxy and rocketry? For context, the Saturn V, which took humanity to the moon, stood at 110.6 meters tall, so Starship is significantly larger.
Right. With the latest design blocks, it's pushing toward 124 meters now, isn't it?
Yeah.
It is. But the real engineering story here, it's not the height. It's the power it generates versus the payload it intends to carry.
The power differential is just immense. Saturn V produced, about 7.6 million pounds of thrust?
That's right. And Starship, when it's optimized for a reusable mission profile, is generating approximately 82 to 90 meganewtons.
Which translates to?
That's 18 to 20 million pounds of thrust. We are talking about generating 2.5 times the raw power of the Saturn V.
Wow.
And that raw power allows Starship to lift a target of 200 tons to low Earth orbit while remaining fully reusable.
And that's the key. The Saturn V could put 140 tons into AO, but it was completely expendable. You just scrapped the entire stack after one use.
Precisely. Starship's reusability is the true economic game changer. It transforms spaceflight from a government luxury into an industrial logistics problem.
But the paradox still lies in the material. Why 304L stainless steel? Every space engineer for the last 50 years has preached lightweight aluminum lithium carbon composites.
Right. Steel is heavy, it's cheap, and it's traditionally reserved for, terrestrial, non-aerospace uses. It seems completely counterintuitive.
It does.
But it's a deliberate engineering trade-off. It's a philosophy built on exploiting steel's unique thermal properties. The sources point to steel's incredible dual resilience when it's faced with extreme temperatures.
So they realized that even though steel is heavier than, say, carbon fiber, they could use thinner walls.
Exactly. Because the steel actually gets stronger at cryogenic temperatures.
Okay, so that's the first extreme, the cold.
Right. The liquid methane and liquid oxygen propellants are super chilled, down to around minus 162 degrees Celsius.
And a lot of materials would just become brittle at that temperature.
They'd risk fracture under pressure. But steel, particularly this 304L alloy, resists that brittle fracture and actually increases its yield strength. So the tanks are far less likely to shatter under the immense internal pressure of the cryopropellants.
And then you immediately pivot to the exact opposite extreme, the heat of reentry.
Exactly. When the vehicle screams back through the atmosphere at hypersonic speeds, friction generates an inferno. Steel retains its structural integrity up to about 800 degrees Celsius.
Whereas aluminum, the traditional choice, just melts around 660 degrees.
Right. And this huge difference in thermal tolerance allows Starship to rely on a much thinner and therefore a much lighter thermal protection system or TPS.
So they took a penalty on the whole mass by choosing steel, but they gained a much larger, much more critical mass saving on the heat shielding because they needed fewer tiles.
It's an elegant solution, almost deceptive, and it makes manufacturing radically cheaper and faster. Steel is available everywhere. You can weld it in conventional facilities, and the cost difference compared to aerospace-grade carbon composites is just astronomical.
It's really central to their whole high-cadence iterative philosophy.
It is.
So if the steel hull is the structure, then the Raptor engine is the beating heart. And it's an incredibly complex heart, pushing the very boundaries of material science.
We're talking about the full-flow staged combustion, or FFSC, cycle. For those listening, this is what gives Starship its immense power density.
And to really understand the complexity, you have to contrast it with, well, basically every traditional engine used in Western rocketry, like the Merlin on the Falcon 9.
Exactly. Those traditional engines, they use a small fraction of the propellant to power the preburners, which spin the massive turbopumps. And the exhaust gas from those preburners is then often just wasted, dumped overboard.
So you're literally just venting energy and mass that could otherwise be giving you thrust.
Precisely. Raptor, with its FFSC cycle, completely eliminates this waste. It uses two dedicated preburners, one burning oxygen-rich, one burning fuel-rich.
And crucially, the exhaust from both of them goes into the main combustion chamber.
Yes. This means 100% of the propellant flow, both the fuel and the oxidizer, passes through the turbines and then through the main chamber. This dramatically increases the chamber pressure and, critically, the efficiency, the specific impulse.
It seems like such an obvious gain in efficiency. Why hasn't this been done before? Why is this the first operational full-flow staged combustion engine?
Because it introduces an incredible metallurgy barrier. Just think about the oxygen-rich side of that turbine assembly. It's not just spinning incredibly fast.
I mean, the latest Raptor 3 designs are pushing the turbopumps well over 30,000 RPM.
Right. It's doing that while being immersed in hot, high-pressure gaseous oxygen. And oxygen is a powerful oxidizer.
So you have high pressure, high heat, and 100% oxygen. It's an environment where the metal itself can literally become the fuel.
Precisely. If there's the slightest flaw in the metal, if a seal fails, or even if a microscopic piece of debris strikes a turbine blade, that metal can ignite and oxidize instantly.
A catastrophic failure.
It's called a turbopump fire. The pump consumes itself in milliseconds. This required them to develop proprietary superalloys metals specifically engineered to be inert in that high-pressure, oxygen-rich environment. And that's a material science challenge that took decades to solve.
So given that incredible complexity and the razor-thin margin for error in the FSC cycle, what are the primary points of failure they're still working on, according to the sources?
Well, the main ongoing challenge is combustion stability and longevity, especially in the extreme environments of a fully reusable engine.
Right.
When you push the chamber pressure this high, even minor fluctuations can lead to high-frequency combustion instabilities, essentially a small internal explosion that can destroy the engine from the inside.
And I imagine the bearings and seals in those high RPM turbopumps have to be perfect.
They have to be unprecedentedly reliable. A tiny piece of shrapnel traveling at those speeds is basically a cutting tool.
And this incredible concentrated power is then multiplied 33 times on the super heavy booster.
That's the thrust aggregation. 33 Raptor 3 engines, all firing in a perfect coordinated sequence, generating around 17 million pounds of thrust. The sheer mechanical coordination required just to lift that 5,000-ton vehicle off the pad and keep it stable is a challenge in and of itself.
We have to talk about what happens when those 33 engines ignite. The acoustic violence generated by Starship isn't just loud, it's a physical assault.
The energy released is hard to grasp because the decibel scale is logarithmic. The Saturn V, famously, hit 204 dB. Starship is pushing well beyond that.
I saw some of the data from IFT-5. Even 6 miles away, specialized microphones recorded sound pressure levels of 125 dB.
And that's louder than a thunderclap or a power drill operating right next to your ear at a distance of 10 kilometers.
So what are the estimated levels closer to the base of the tower?
At the 0-meter mark, the acoustic energy is estimated to exceed 145 to 150 dB. At that point, the air stops behaving like a fluid medium and starts behaving like a compressible solid.
Wow.
We're talking about shock waves that can cause physical damage, not just hearing loss. Sources say these levels can induce pulmonary embolisms, rupture hollow organs, and cause catastrophic damage to unshielded infrastructure.
That makes me wonder about the first crew briefing. Do they just hand you high-pressure earplugs and say, good luck? What do the sources say about acoustic dampening inside the crew stack, 120 meters up?
Inside the crew compartment, the main threat isn't the airborne sound, it's the structure-borne vibration. Engineers have to heavily damp the vibration paths between the engine bay and the crew tiers.
But even with dampening, those immense low-frequency vibrations must penetrate the body.
They do. And this is where the concern about pogo oscillation becomes acute.
Explain pogo oscillation again and how they fight it.
Pogo is this terrifying, self-sustaining feedback loop. The engine thrust, which isn't perfectly constant, excites the resonant frequency of the massive fuel columns inside the tanks. This vibration changes the pressure and flow rate of the fuel going into the turbopumps, which in turn alters the thrust output, perpetuating and amplifying the vibration.
So if you don't stop it.
Left unchecked, the G-forces caused by pogo could easily lead to catastrophic structural failure, or at the very least, shake the crew into unconsciousness and damage delicate avionics.
So how do you dampen an internal earthquake?
They use a combination of techniques. One is the use of accumulators, basically large shock absorbers, placed near the engine injectors that absorb pressure fluctuations before they feed back into the main flow.
And there's an active component too, right?
Yes, active dampening through flight computer control.
Yeah.
It subtly throttles the engines to counter the measured vibration frequency. It's this intricate, real-time dance of physics and software just to keep the internal forces from tearing the stack apart.
And we can't forget the crackle, that high-frequency popping sound that witnesses report.
That's the sound of extreme speed in the exhaust plume. The high-velocity gases moving over 3 kilometers per second create and immediately collapse millions of miniature vacuum pockets along the plume's shear layer.
And each collapse is a tiny sonic boom.
Exactly. When you multiply that across 33 engines, it results in that terrifying, visceral crackling sound that has become the signature of Starship.
Starship's developmental history is just. It's intrinsically linked to explosion. And this brings us to the core philosophy driving the program: iterative design.
Or fail fast, learn faster. It's an approach to rocketry that accepts spectacular failure as a necessary data point.
It's a radical cultural shift away from the traditional risk-averse government-led programs that prioritize theoretical safety above everything else.
Right. They are choosing to have these explosive disassemblies on the test stand because they believe it rapidly accelerates the learning curve, which ultimately makes the final flight safer. We have to view the flight test data as a timeline of specific lessons learned.
Okay, so let's review those lessons. IFT-1 in April 2023, that was the infrastructure disaster. The concrete pad was just disintegrated, hurling massive boulders into the Gulf.
And that taught them the need for a water deluge system and a massive flame deflector, an engineering necessity they had initially dismissed.
But critically, that first flight proved that the stainless steel structure, even while it was tumbling wildly during flight termination, could survive max Q, the peak aerodynamic stress.
That was a huge validation of the whole design, a massive win from a massive failure.
Then IFT-3 in March 2024 was key because it achieved that mission prerequisite, demonstrating propellant transfer technology in space.
Exactly. Even though the ship broke up later during an uncontrolled reentry, the fact that they successfully moved cryopropellants between tanks and microgravity was the single most important technical data point they needed for the Mars mission concept to be viable. It proved the hardware worked in orbit.
And in IFT-5, October 2024, was the turning point for the entire architecture. The successful return and mid-air catch of the super heavy booster by the chopstick arms of the 𝐏𝐻𝐃𝐂𝐀𝐒𝐓 tower.
That maneuver, the 𝐏𝐻𝐃𝐂𝐀𝐒𝐓 catch, is the economic engine of Mars colonization. Proving that you can rapidly and reliably recover that massive hot booster eliminates the need for expensive recovery barges and complex landing legs.
The chopsticks act as both the launch mount and the catching mechanism,
Which compresses the turnaround time and slashes the cost per kilogram to orbit.
but isn't relying on 33 engines and this single, incredibly complex catching mechanism, creating a kind of combinatorial risk that negates the benefit of reusability. Where did the sources weigh in on that?
The sources absolutely acknowledge the risk aggregation is high, but the argument is that the benefit, that ultra-low cost per launch, outweighs it.
But we've seen how thin the margins are.
We have. Consider IFT-8 in March 2025. That flight ended with the upper stage disintegrating because of a tiny hardware failure in a single-center Raptor engine. It just proved that even with robust systems, the margin for error remains razor-thin. One component failure can lead to the destruction of the entire 124-meter stack.
It's the ultimate high-wire act. The crew, when they eventually fly, are trusting their lives to a machine that has failed publicly multiple times. Yet those failures have provided the necessary data to proceed.
It's a paradox.
Let's shift our focus to the human element riding this colossal structure. Imagine being one of the 100 people stacked in tiers inside the Starship payload section, waiting for T-0. What is that sensory experience like for those initial 3 minutes?
The initial experience is defined by this rigid choreography of noise and vibration. The crew is lying in their seats, knees bent, facing the sky. First, it's the mechanical hum of life support, the whine of the avionics, and then the deep physical shockwave of the 33 engines igniting.
The sound hits the body through the structure long before it reaches the ears through the air.
Oh yeah, it's a violent, non-negotiable shove into the seat restraints.
And the acceleration curve is fascinating, isn't it? It starts so ponderously slow.
That's due to the sheer mass, 5,000 tons, fully fueled. Initially, the G-force builds slowly, 1G, 1.5G, 2G. But the vehicle is shedding propellant at an astonishing rate.
So as the mass drops exponentially, the constant thrust means the acceleration climbs dramatically.
Reaching peak G-forces towards the end of the booster burn.
And about a minute into that climb, they hit max Q, maximum dynamic pressure.
Max Q is the structural torture test. This is where the speed of the rocket and the density of the atmosphere combine to create the peak aerodynamic load. The steel hull audibly groans under this extreme external compression.
For the crew, this has to be the moment of maximum vibration and physical discomfort.
Absolutely. Before the air thins out and they transition into the relative smoothness of the upper atmosphere, this is when the automated systems are working overtime to compensate for those aerodynamic stresses.
Then, at approximately 2 minutes and 40 seconds, the super heavy booster engines cut off MECO, and the crew experiences this moment of profound, almost unnerving silence.
A silence that lasts only a fraction of a second before the critical, high-stakes, hot staging maneuver.
Hot staging is where efficiency meets controlled chaos. It's critical because the upper stage engines, the 6 Raptors, ignite while still physically attached to the booster.
Right. The exhaust from those engines blasts directly onto the interstage section, forcibly pushing the spent booster away.
But why introduce that incredible violence and risk? Why not just separate cleanly, then light the upper stage?
It's purely about efficiency and propellant management. It's often called ullage maintenance. If you separate first, the ship is in free fall for a moment, and the liquid propellants, the methane and oxygen, will slosh and float away from the pump intakes in 0G.
So by igniting the upper stage slightly early, the thrust keeps the propellant settled at the bottom of the tanks.
It ensures a clean, continuous fuel flow for that second stage burn.
But the margin for error is absolute zero.
Correct. A delayed or non-ignition means the upper stage fails to separate and falls back to Earth, breaking apart. An asymmetrical ignition, where one engine lights before the others, sends the entire vehicle into a lethal, unrecoverable spin. It's a minute, long sequence of pure, unforgiving physics.
So once that upper stage burn is complete, they're floating in low Earth orbit, having achieved 27,000 kilometers per hour. The violence is ended, replaced by microgravity. They're in the parking lot of the cosmos.
But they are stranded.
Exactly.
A single Starship launch, even with its colossal power, only provides enough delta V, that's the change in velocity, to get itself and a minimal payload into LEO. To escape Earth's massive gravity well and achieve the necessary velocity change for a Mars injection, well, the ship needs to be virtually 100% full of propellant.
And this brings us to what is arguably the most challenging engineering feat of the entire Starship program. Orbital refueling. This is the linchpin, the economic engine of the Mars mission.
The entire Mars architecture relies on this delicate, demanding ballet. The Mars-bound ship has to be met in LEO by a sequence of specialized tanker starships. They have to rendezvous, match velocity, and perform a stable tail-to-tail docking.
Which is difficult enough with delicate instruments.
But then comes the transfer of hundreds of tons of super-chilled cryogenic propellant.
So how do they handle the challenge of transferring fluid in zero gravity?
This is the critical vacuum challenge. In 0G, fluids form these spherical globules and just float everywhere inside the tank. They won't naturally settle at the pump intakes.
So the ships have to, nudge themselves?
They have to execute precise, small bursts of ullage, thrust from their internal thrusters, to gently accelerate the entire ship for a moment. This settles the liquid methane and oxygen at the bottom of the tanks, allowing the pumps to engage and transfer the propellant cleanly.
And beyond the physics of fluid management, there's the logistics and reliability challenge. We're not talking about one extra tanker. The sources suggest anywhere from 4 to 16 separate tanker flights are needed.
Depending on the payload mass.
Right.
Just think about the combinatorial failure rate. Each of those 4 to 16 launches has its own risk: a launch anomaly, a Mechazilla failure, a docking failure, a leak during transfer.
Or a radiation event while they're just waiting in ELEO.
Exactly. If the refueling chain breaks, the Mars ship is stranded. And physics dictates that the launch window, the home and transfer opportunity, only opens once every 26 months.
So if the 14th tanker flight fails, the crew might have to wait over 2 years in low Earth orbit, just consuming life support resources, dealing with the accumulated radiation exposure, all to wait for the next launch window.
Absolutely. The margin for error is astronomical, and the timeline is unforgiving. It's an extraordinary example of a cascade failure risk, where the economic benefit of the reusable architecture is directly tied to the complexity of a never-before-attempted orbital logistical operation.
So once they are fully fueled and the planets align, they fire the engines one last time for Transmars injection, and they coast into the black. This journey is dictated by orbital mechanics, lasting 6 to 9 months.
This is the long dark. No engine noise, no possibility of a quick return. The ship might be gently rotating for thermal equilibrium, but otherwise it's just coasting. This is where the psychological filters really begin to apply.
Earth shrinks first to a bright star, and then it's just a pale blue dot receding into the void.
And the sources reference the breakoff phenomenon.
Yeah.
This is the irreversible psychological detachment from the planet of origin. You realize the air you breathe, the food you eat, the water you drink, everything necessary for life is completely contained within this pressurized metal cylinder. And the distance between you and the nearest hospital is measured in millions of miles.
The crew is utterly reliant on their own resources. And psychologically, that cultural safety net of Earth is severed forever.
It is.
And space is not a vacuum, it's a particle accelerator. The crew faces ionizing radiation, which presents two very distinct threats that require radically different countermeasures.
The first are solar particle events, or SPEs. These are bursts of high-energy protons ejected suddenly and unpredictably from massive solar flares.
Sporadic, but they could be violent enough to deliver a lethal acute dose of radiation in just a few hours.
So the immediate response is a race to the storm shelter.
And Starship's design integrates that shelter, likely using the ship's stores, food, and water as shielding.
Water, being rich in hydrogen atoms, is highly effective at absorbing those relatively lower energy protons that make up the bulk of an SPE. The water stores provide necessary mass shielding.
But the SPEs are, in a way, the easy threat to mitigate because they're episodic and simple to block.
The true long-term threat is galactic cosmic rays, or GCRs.
These are the heavy nuclei, iron, carbon, silicon accelerated by supernovae outside our solar system to near light speed.
And because of their massive kinetic energy, they just slice through thin layers of shielding like a hot knife through butter. And this introduces the problem of secondary radiation.
Okay, explain that.
When a GCR strikes the hull or the water shield, it doesn't just stop. It shatters the atoms in the shielding material, creating a shower of secondary particles, primarily neutrons, which scatter throughout the crew compartment.
So thin shielding is actually worse than no shielding because you're creating high-speed biological shrapnel inside the cabin.
That's an excellent way to put it. These secondary neutrons are biologically even more damaging than the original primary ray because they're less energetic but more ionizing when they hit human tissue.
Let's quantify the cumulative risk over the 6-month journey. The annual background radiation on Earth is about 3 millisV. What kind of dose are they taking on Starship?
A single transit exposes the crew to approximately 300 to 500 millisV.
Wow.
And if you look at the full mission around trip plus a surface day, the cumulative dose easily pushes past 1,000 millisV. This significantly exceeds NASA's current career limit for increased lifetime cancer risk. The commitment is absolute, even biologically.
And the risk isn't just cancer decades later. It's the immediate neurological threat, the so-called space brain.
Yes, the heavy ions of the GCRs are physically traversing neural tissue. Studies on mice exposed to GCR analogs show alarming results. Measurable reductions in the complexity of dendrites, the branches that neurons use to communicate.
And this translates to what? Actual cognitive impairments.
Measurable ones, including memory deficits, compromised executive function, and increased anxiety. They arrive at Mars already physically and potentially cognitively impaired, having been hit by a continuous invisible hailstorm.
The psychological cost of absolute confinement over 6 to 9 months is the third great filter. We have decades of analog data from simulations like Mars 500 and the 𝐏𝐻𝐃𝐂𝐀𝐒𝐓 habitat in Hawaii, What do those sources tell us about how human groups deteriorate over time when they're locked in a box?
The data is consistent. Human groups confined in isolation show a predictable pattern of decline. Statistically, the most challenging period is the third quarter phenomenon.
This is when morale just plummets,
Yeah.
right? Just past the halfway point.
Exactly. The excitement of the launch is faded, the routine is monotonous, but the end destination is still too far away to provide motivation. This is when minor irritations escalate into toxic interpersonal conflicts.
And Starship concentrates those stressors intensely. It's a closed-loop system where you cannot walk away from a conflict.
It's a pressure cooker. We're talking about the lack of privacy, the constant mechanical hum of life support, the smell of perpetually recycled air, and disrupted sleep cycles due to the lack of natural light cues.
Not to mention the sensory phenomena like seeing flashes of light with your eyes closed.
Right, caused by GCRs hitting the retina. All of this combines to just erode psychological resilience.
The ultimate stressor, though, is imposed by physics, the communication lag.
The light lag to Mars ranges from 3 minutes when the planets are closest to over 22 minutes one way when they are on opposite sides of the sun. This renders mission control largely irrelevant in an emergency.
By the time Houston hears the problem and formulates a response, the situation is fundamentally changed.
Or the crew has already died.
This means the command hierarchy is fundamentally inverted.
Absolutely. The ship must be fully autonomous and the crew must be fully autonomous. The command structure shifts from a hierarchy reporting to Earth to an isolated, self-governing unit. And this raises genuine ethical and psychological concerns about decision-making under stress.
If the crew splits on a critical interpretation of mission rules, or if internal conflict escalates, there's no option for external intervention or retreat.
They are their own ultimate authority.
Finally, we address microgravity. The human body adapts with ruthless efficiency, and in the absence of gravity, it begins to shed everything unnecessary, including bone and muscle mass.
The core issue is bone density loss, particularly in the weight-bearing bones of the hips and spine. It drops 1 to 2% per month. And the body, trying to compensate for this loss, flushes the excess calcium into the bloodstream,
which significantly increases the risk of kidney stones.
Dramatically. And a kidney stone in 0G is a life-threatening medical emergency. Microgravity surgery is functionally impossible because blood just floats out and contaminates the cabin, risking infection and blindness.
And the heart shrinks, cardiac atrophy.
Right, because it no longer needs to fight Earth's gravity to pump blood, making the crew vulnerable to fainting upon arrival at Mars, which has 0.38 G.
So what are the primary countermeasures they have to employ just to arrive in a functional condition?
Intense discipline exercise protocols are mandatory. The crew has to spend hours a day on specialized treadmills and resistive exercise devices designed to mimic the resistance of gravity. They also need sophisticated medical monitoring for calcium levels.
But perhaps the most persistent mystery is SANS, spaceflight-associated neuroocular syndrome.
SANS, yeah. When you remove gravity, fluids shift to the head, increasing the intracranial pressure. This pressure acts on the back of the eyeballs, flattening them and causing the optic nerve to swell.
The result is farsightedness and blurred vision,
which severely impacts a crew's ability to perform precise technical maneuvers during landing. And the sources are still debating the long-term reversibility of this damage. It is entirely possible they will arrive at Mars visually impaired.
So we have this incredible paradox. The crew endures acoustic violence, a 6-month radiation assault, and the psychological burden of isolation, only to arrive physically weaker, brittle-boned, and visually impaired just before the most technically and physically demanding sequence of the entire mission, the Martian descent.
It's a daunting prospect.
Let's pivot to the landing sequence. The Mars atmosphere is often described as a cruel joke. It's thick enough to generate catastrophic friction, but far too thin, about 1% of Earth's density, to provide effective braking.
And they hit that atmosphere at 7.5 kilometers per second, over 16,000 miles per hour.
This speed necessitates Starship's completely unique belly flop entry.
Instead of entering nose or base first, like a traditional capsule, Starship performs this high-drag maneuver at a 60-degree angle of attack, presenting its entire vast underbelly to the airstream. The goal is to maximize drag to shed velocity, relying entirely on the thermal protection system,
the TPS, which brings us back to those 18,000 hexagonal silica tiles. Why are the geometry and shape of those tiles so crucial here?
The hexagonal shape is an engineered countermeasure against the propagation of thermal failure. If you had tiles with straight edges, if one tile cracks or fails, the superheated plasma, which can reach 1400 degrees Celsius, can accelerate through that gap and basically unzip the shield.
allowing the plasma to cut through the steel hull underneath like a plasma torch.
Exactly. The hexagonal geometry forces the plasma flow to stall at the corner joints, isolating the failure.
But the weak points remain. Where do the sources indicate the greatest risk lies during entry?
The hinges and complex geometry around the forward and aft aerodynamic flaps, the moving parts, the tiles have to interact with those dynamic components, which creates unavoidable gaps where plasma can seep in.
But the greater challenge is the condition of the tiles before entry.
The launch damage.
Right.
The extreme acoustic vibration and mechanical stress of the launch and staging maneuvers can cause tiles to fall off in LEO. The sources highlight this unresolved challenge. Starship must have an EVA capability, a spacewalk to inspect and replace missing tiles before Mars entry.
A missing tile is a fatal flaw.
And this is a capability routine in-orbit tile inspection and repair that has not yet been reliably demonstrated.
And for those 7 minutes of maximum heating and stress, they are blind.
The entire ship is enveloped in superheated plasma, which blocks all radio communication. The crew is alone, trusting entirely to the automated flight computer. This is the 7 minutes of terror redux, but with a far more fragile, high-surface area vehicle.
And because Mars's atmosphere is so thin, Starship approaches the ground at a dangerously high terminal velocity. It can't slow down to a gentle subsonic speed like it can on Earth.
And this necessitates the most critical final sequence.
The famous flip and burn.
Right. The final few hundred meters of descent require the ship to transition violently from a horizontal, high-drag orientation to a vertical one. And then the Raptors have to ignite supersonically.
Supersonic ignition. Why is that so notorious?
Igniting a highly optimized combustion chamber while high-speed air is flowing into it is an extreme challenge for combustion stability. It risks hard starting, where the flame front violently oscillates, or chugging, where the pressure pulses risk damaging the engine.
The precision here has to be absolute.
If the engines hesitate for a fraction of a second, or if the flip maneuver is mistimed by milliseconds, the ship impacts the surface instantly. There is no recovery time.
Even if they execute the flip and burn perfectly, they still face the ground hazard created by the total lack of infrastructure.
Exactly. The initial missions are landing on unpaved Martian regolith. The immense thrust required for braking will kick up a massive storm of abrasive rock and dust.
This creates several risks: engine erosion, damage to the skirt of the ship, reduced visibility.
And furthermore, there's no flat, prepared landing pad. If the ship tips on a single large rock, or if the soil is unexpectedly soft, the mission ends. A tipped Starship cannot take off, and the crew faces a slow, asphyxiating tragedy millions of miles from help.
Assuming a successful landing, survival dictates immediate action. The first, non-negotiable priority isn't shelter. It is manufacturing the propellants needed to leave. In-Situ Resource Utilization, or ISRU.
The Mars mission is only viable if the colonists can create methane fuel and oxygen oxidizer from the local resources. They have to rely on the highly energy-intensive Sabatier reaction.
So for our listeners, let's break down the chemistry of the Sabatier reaction into conversational steps.
Okay, so first, they have to harvest the main ingredient, carbon dioxide, PEX CO2, from the thin Martian atmosphere. Second, they need hydrogen, which they have to get by mining and melting water ice found in the Martian soil.
And then they combine them.
Third, they combine the TEX-TA2 and TEX-T2 in a reactor using heat and a catalyst to produce methane for fuel and water as a byproduct.
And then that byproduct water is key.
It is. Finally, they take that water and use electrolysis to split it back into hydrogen, which cycles back into the reactor, and oxygen, which is essential for breathing and for the rocket's oxidizer tank.
So they are literally building their ship's return ticket molecule by molecule on the surface of another world.
Yes.
But this entire process just screams for continuous power. And Mars only gets about 40% of Earth's solar flux.
That is the ultimate bottleneck. To produce enough propellant to refuel a Starship for the return journey, we're talking about hundreds of tons. It requires megawatts of continuous power.
And solar panels are just not going to cut it.
Not reliably. Even acres of them are subject to low sunlight and constant dust accumulation. The most reliable solution, as detailed in the sources, is the deployment of nuclear fission reactors, like the kilopower units. Without that powerful, reliable energy source, the propellant production freezes and the lifeline back to Earth is severed.
Once a fuel factory is running, where do they live long term? The Martian surface is a radiation hazard zone, even without a solar flare, about 0.7 millisV per day of exposure.
The landed Starship structure is insufficient shielding. Long-term survival demands going underground to shield against the persistent galactic cosmic rays, and the sources discuss 3 primary methods for achieving that deep shielding.
The romantic ideal: lava tubes.
Natural volcanic caves. They offer superb shielding and thermal stability. They are the ideal natural habitat. However, finding an accessible entrance and then engineering the massive airlock and sealing technology required to pressurize a geological feature that large is an enormous high-risk endeavor.
The more pragmatic option is cut and cover.
This is a life of moles. Autonomous rovers dig deep trenches. The crew places inflatable habitats inside structures designed to maintain pressure and air quality. And then they bury those habitats under several meters of Martian regolith, using the soil itself as radiation shielding.
And you need several meters for adequate GCR protection,
which requires significant, sustained robotic construction before the crew even arrives.
Regardless of the habitat, the long-term biological consequence of life in 0.38 G is the most profound consideration. Let's talk about the divergence. Homo martis.
We have no definitive data on human embryogenesis in partial gravity, but physics is unforgiving. Mars gravity is slightly over 1/3 of Earth's. Children born there would likely grow taller due to reduced spinal compression, but their bones would be thinner and more brittle.
And crucially, their hearts, adapting only to the lower work requirements, would atrophy.
And this creates a biological exile.
It does. Could a human born and raised entirely in 0.38 G ever withstand the gravity of Earth?
Their skeletal structure might be too fragile, their cardiovascular system too weak to pump blood efficiently against 1 G. They become a distinct subspecies, Homo sapiens martis, biologically bound to the red planet, unable to return to the world of their ancestors.
Why accept the absolute risk of brittle bones, chronic radiation exposure, and biological exile? This takes us into the philosophy of the mission, starting with the chilling concept of the Great Filter.
The Fermi paradox asks the profound question. In a universe billions of years old with countless habitable planets, where is everybody? The Great Filter is the theory that there is some stage in the development of life, either incredibly difficult to pass or impossible, that explains the silence.
And the most terrifying conclusion is that the filter lies ahead of us.
If you look at the historical timeline, human civilization has developed the technology for self-annihilation, nuclear war, engineered pandemics, but we have not yet achieved true multiplanetary status. The filter might be self-destruction before technological maturity.
So Starship is framed as the ultimate insurance policy, an attempt to back up the drive, bifurcating the timeline of human extinction.
It is spreading the risk. The core rationale is that if Earth faces an inevitable catastrophe, whether it's natural or self-inflicted, the light of human consciousness and culture does not go out entirely. Mars becomes a highly volatile yet absolutely necessary guarantee for the long-term survival of the species.
This philosophical justification meets strong criticism, though. The counter-argument is that sending humans to die on a frozen radioactive rock is unethical, diverting enormous technical and financial resources away from urgent crises here on Earth: climate change, global poverty.
That is the essential societal debate. However, the counter-narrative from the volunteers and proponents is centered on the concept of absolute commitment. They view themselves not as colonists taking resources, but as envoys expanding the frontier of self-sufficiency.
For them, the high risk, the implicit one-way nature of the journey, is a necessary feature.
It forces the immediate creation of a sustainable civilization. It's the ultimate act of burning the ships.
And that commitment extends to the grim reality of ultimate self-reliance, deep space medical triage, where Houston can't help.
The challenges are extreme and unforgiving. Imagine internal hemorrhaging during a sudden event, where gravity is either absent or too weak to manage blood loss and surgery. Imagine a highly virulent virus spreading instantly through the sealed, closed-loop air system. Every routine Earth-based medical safety net just vanishes.
This brings us to the existential shadow of the one-way ticket. The discussion in the sources about end-of-life care is profound. Does the medical kit include palliative care, perhaps the exit pill, for untreatable, fatal conditions in a zero-G, zero-option environment?
That decision-making power must reside entirely with the autonomous crew. The light lag forces them into a position of absolute moral and legal authority over their own lives and the lives of their colleagues. They are forced to establish and execute life-and-death medical protocols with no external oversight or second opinion.
This isn't just about technical skill.
No. It's about unparalleled moral fortitude and autonomy.
So as we synthesize our deep dive, Starship is the ultimate engineering contradiction. A powerful, reliable machine of stainless steel, built through failure, yet flying toward a 6-month biological and psychological razor's edge.
The risk is absolute. 1,000 plus millisieverts of chronic radiation, the crushing isolation of the third quarter phenomenon, brittle bones, impaired vision, and zero-margin critical landing maneuvers. Starship represents the industrialization of space. It swaps the clean white romance of Apollo for the deafening roar of methane combustion and the grinding necessity of self-reliance on a world that actively tries to kill you. When that first Starship lands or crashes, humanity will have forever changed its own definition of survival.
And we've established that because Houston, we have a problem, is functionally impossible, the crew must become their own ultimate governing body, setting their own rules for survival and deciding life and death medical triage. The potential for divergence under stress or even mutiny when faced with a 22-minute communication lag is a real structural risk built into the very physics of the mission. And this raises a final provocative thought for you, the listener. If the crew is designed to be fully autonomous, capable of deciding critical medical and ethical protocols with minutes-long lag to Earth, what kind of person would you trust to lead that final, irreversible journey into self-governance?